We previously looked at the translations, the slides of parabolas moving left and right and up and down. Worked exactly the same way as it did for the absolute value functions that we had studied. And so, of course, we can also dilate and reflect parabolas just like we could those other types of functions. And so, taken together, those translations, adding or subtracting something on the inside of the parentheses to move the graph left and right, adding something on the outside of the parentheses, moving the graph up and down, along with the introduction of a coefficient out in front here that we'll call a. And so taken together, when an equation of a parabola is written in this format, where we've got the a out front here, we have a number being added or subtracted on the inside, we have a number that's being added or subtracted on the outside, we call this the vertex form of a parabola. And so we can, similar to something like y equals mx plus b, we can identify all of the key features that we need of a parabola just by looking at the equation, and then use our previous knowledge about the shape of a parabola, the proportions of it, from the vertex to be able to accurately sketch its graph. So the vertex is going to be the hk. So h is the number that's being subtracted from x, so it's going to be the opposite of the positive negative sign that we see. So if that said x minus 4, we would have positive 4 as our x coordinate. K then here is going to be the y coordinate of our vertex, and then to determine whether the graph opens up or down, and then how wide or narrow the parabola is compared to our standard, we're going to use that value a. If it's negative, it opens down. If it's positive, it opens up. And then we'll see how that affects the width here through a few examples. But again, when an equation of a parabola is written in this format, we can use all of that information, the a and then the h and k, to be able to come up with the graph relatively quickly. So let's put that vertex form into practice here. So first thing we're going to do is we're going to identify the transformation, so what all these numbers in our equation do. Then we're going to identify the location of the vertex, and then we'll get a sketch of our graph. So to start off with, we'll go with the familiar. So we've got these two numbers that are on the inside here. So we can say that our graph is going to be translated. So that minus 5 moves us left and right, opposite of what we would expect. So minus 5 is going to move us to the right 5 units. And then that minus 8 moves us in the vertical direction, but that is the way that we would expect. So we're also going to get translated down. It's a U or a W there, sorry. Down 8 units. And so that there is my vertex. So I'm not considering the 2, that's not affecting my vertex at all, it's just going to affect the width of my graph. But that 5 right and 8 down is going to give me the vertex. So I'm going to move to the right 5, go down 8, and so there is the point of my vertex. Now we have another transformation that has taken place here. So that's as a result of this 2. And so the way we describe that is like we did with our other functions. We're going to say our graph is dilated by a factor of 2. So what does that mean for our graph? Well, normally our graph would go over 1, up 1 in both directions from the vertex. And then the continuation of the pattern would be over 2 from the vertex, up 4. And then we'd go over 3 and up 9, which would put us up here. So that would be the normal set of points that we would have as a result of the parabola, for the parabola. But because we have this 2 that's out front, because we have that dilation factor, what that's going to do is it's going to double all of the ups, so to speak, in our pattern. So instead of going to the right and left 1 and up 1, we're still going to go to the left and right 1, but now we're going to double that and we're going to go up 2. So we have our vertex down here. we're going to go left and right 1, but because of that dilation factor, we're going to go up twice as far. So we're going up 2 instead of just 1. Likewise for the next set of points, instead of going over to the left and right 2 and up 4 from the vertex, we're going to go to the left and right 2, but now we're going to go up 8 from the vertex. So I'm going to go over 2, up 8. That puts me here and here. And then again, I'm going to go over left and right 3, but I'm not going to go 9 up. I'm going to go up 18. So all of my ups, all my outputs are being doubled. So if I go up 18, so I'm going 8 up to get to the x-axis and another 10. So that gets me up to here. So what we can see is we have a parabola that goes up faster than the original set of points would have been were it not for the fact that that 2 is there. So the dilation in this case, that factor of 2, stretches us in the vertical direction. It pulls us upwards faster. So the result is we have a narrower parabola. It's going up more quickly than the set of points that we would have had were it not for that 2. And then the last thing that I have here is the domain and range. So we've talked about domain and range before, so I want to revisit that here in the context of these parabolas. So if you'll remember, domain is a question of what x values are you allowed to plug into your function, or what x values does your graph include. Now in the case of a parabola, it's very similar to those V-shapes, where the graph just keeps getting wider forever. Now it's getting steeper as we go, but it's never going to go totally vertical. So if we extend to the right forever and to the left forever, if this graph is indeed going to keep getting wider and wider and wider, it will eventually encompass all of the possible x values. So our domain is all real numbers, or if we want to shortcut that, we have our fancy r that we can make to represent that. Now in the vertical direction for the range, that's not the case. This graph does extend upwards forever, but it does not go down forever. It has a floor. And so that floor right here is going to be whatever the y-coordinate of the vertex is. That in this case is the lowest point that this graph ever hits. So my range in this case is going to be y is greater than or equal to -8. So whatever the bottommost point of my graph is, that's my floor, and then I'm going up forever from there. So in this case, y is greater than or equal to -8. This parabola was opening downwards. If it was upside down, as we'll see in a subsequent example, then that would be the highest point, so then y would be less than or equal to whatever that value is. But we'll see that in a future example.